In this video, we're going to explore a couple reaction mechanisms involving electrophilic aromatic substitution. It's strictly a mechanism video. We're going to provide a mechanism for each reaction below. Here we're starting off with the chlorination of benzene using chlorine and iron. Some of you may be saying to yourself right now, wait, where's the iron chloride catalyst? The truth is, chlorine is so reactive, and you're all familiar with the the reaction that iron undergoes over time in the air. It undergoes rusting with oxygen. Oxygen's a strong oxidizer. Chlorine is an even stronger oxidizer. It oxidizes iron instantly in this reaction, where you don't have to show me the mechanism. You just have to know it happens. Chlorine will oxidize iron to iron's highest oxidation state, which is iron plus 3. So iron reacts with chlorine to make iron 3 chloride. For the purists out there, we will balance this, something organic chemists rarely do. 3 of those. 2 of these, make 2 of these. We need to use this catalyst to generate our super electrophile. Chlorine is going to attack the iron chloride in a fashion like this. As seen in the previous video, chlorine, a normally electrophilic species, is forced to act like a nucleophile with the powerful Lewis acid iron 3 chloride. We can save a step by saying next. Chloronium ion is produced here and a complex ion indicated here. Chloronium ion will react with the benzene. I want to put the chlorine on this carbon, so I'll choose a carbon that has a pi electron to that position, and I'll choose a better arrow. This will generate an intermediate that looks a lot like our final product, but it doesn't have this pi bond anymore. It still has the original hydrogen here, and it has a carbocation right here. And that's generated in this step. Benzene becomes a cyclohexadienyl carbocation. I just noticed I mentioned a complex ion and forgot to put the ion on it. That complex ion will provide a chloride that will take the proton off of our intermediate here. Let's see if this looks good. Chloride comes, grabs that H. Don't like how that looks. Did a quick switcheroo on the position of the chlorine and the hydrogen just so these arrows look a little cleaner. And better fix the angles. And we get a pi bond here, generating our final product. So there you have it. If I'm scoring this on a test, 1 point for this set of arrows, 1 point for this set of arrows, that's just 1, so we're up to 2. Another for this set of arrows, 3. Intermediate, 4. And another intermediate here, 5. 5 points. Our mechanism for this larger reaction here and the generation of bisphenol A here illustrates that there are other ways of making electrophiles not covered in our previous video. Epoxides in the presence of acid will protonate and activate themselves. This being phosphoric acid right here. Epoxide protonates, generating an oxonium right here. The epoxide is now activated towards attack by a nucleophile. That would be the benzene. To put a group in the para position, we need a pi bond that's attached to a para carbon. Attack. Normally we have to consider which carbon of an epoxide gets attacked, but here we have identical substitution on both carbons, so we just pick one and attack it, generating this intermediate here. Cyclohexadienyl carbocation, and the conjugate base of phosphoric acid, which miraculously appeared here. It was produced in step 1. And the base picks up a proton, and we resonate and re-aromatize our benzene in a very fast step to generate the first half of our product here. Now we have to generate another electrophile for electrophilic aromatic substitution. Keeping in mind that this position is both tertiary and allylic, means generating a carbocation there should be very facile. Some people say facile. We're going to use the same acid we used before. We regenerated it here. We could put a plus sign here. We're going to protonate it with a lone pair. Generating a new carbocation after a second step. And I believe I forgot to recolorize my 2 steps that I talked about earlier. I'll come back and talk about that in a second. This would be a second step here. Different colors. I will put the color scheme up right now. Both my highlighted arrows here and here need to be blue, because they would only happen after the red arrows happened. And now I fix that issue. And we're going to generate a new carbocation that's very stable. Right here. Let's put it down here. Or rotate it. Carbocation is right here. And another molecule of chlorobenzene is going to attack that, as indicated right here. We got our tertiary benzylic carbocation. We're going to use a pair of electrons that's attached to the para position here. Our whole next video will be about why we're putting this group in the para position. The video will be called Directing Effects. But for now, we just have to come up with a mechanism that gives the indicated product. And this arrow will result in a new intermediate indicated here. Intermediate indicated here will undergo re-aromatization using the hydrogen phosphate ion as the base. Sigma becomes pi, E1 type reaction. And we've made our desired product. End of that mechanism. Point count, 1 point for this set of arrows here, 1 point for this intermediate here, another point for this set of arrows here. We're up to 3. Intermediate 4, arrows 5, intermediate 6, arrows 7, plus 1 for doing 2 steps, intermediate 8, arrow 9, intermediate 10, arrows 11. We don't like the number 11, so we'll call it 12 points somehow. 12 points overall here. This next reaction is very similar to the industrial synthesis of bisphenol A, a molecule which, when added to the manufacture of plastics, tends to soften the plastics, which is often desirable. but later we found out that bisphenol leaches out of the plastics into our bodies and causes endocrine disruption as an estrogen mimic. Enough of that. Mechanism starts by activating the carbonyl towards attack by the benzene, and then the attack by the benzene. In a second step, I will put the color scheme here as well, just to be clear. First arrow and resulting second arrows. Red arrows first, blue arrows second. Generating this intermediate here. We have a cyclohexadienyl cation, and there's where the acetone is now, protonated O. You do a couple things together here. The first thing would definitely be the re-aromatization, always a quick step, second part of electrophilic aromatic substitution. It's an E1 type reaction, and we re-aromatize. Next part, we have to make the O a better leaving group. By protonating it with HOTS. So we're protonating the OH. It would happen after the red arrows. And looking even further ahead, although it's not, oh, it's still, yes, it's going to be the same kind of cation as before. Tertiary benzylic, plus facile. This would be the third arrow. I don't think I have to write down that purple arrow would be third, because it's not first and it's not second. And we generate this intermediate here. This tertiary allylic carbocation will be attacked by a second molecule of phenol. Use the pi electrons that are attached to the para position, and we will make this key intermediate here. Cyclohexadienyl carbocation needs to undergo re-aromatization using the toluene sulfonate generated in the previous step. Toluene sulfonate completing the second catalytic cycle for toluene sulfonic acid by becoming toluene sulfonic acid. There's the re-aromatization step. And there you have it. You've manufactured bisphenol A. Point count, step by step, it was the same type of mechanism as the previous one up here. So I gave it 12 points. And I hope this exploration of electrophilic aromatic substitution mechanisms has been beneficial to you, and I look forward to our next video.